David.
All right, let's get started. Got recording going. Okay, so let's see. It's Tuesday. Problem set 4 is out. End of the week. Any questions or problems? Okay. All right. Last time we started talking about graphs, and one thing we talked about was depth first search. Oh, sorry.
So sorry.
We have an announcement I forgot about. Sorry about that.
Sorry. I'm just with Women in Computing, and we're having an event February 13th, 2 to 3 o'clock with a Google software engineer, and it's about imposter syndrome. So can I write the room number on the board? Okay, cool. So I'll just write it up here.
Right over here.
Or with a marker. It's, yeah. And yeah, and it's not just open to women, it's open to everybody. So just
Okay, so in case you didn't, she said it, it's Women in Computing talk about imposter syndrome, but what is imposter syndrome?
It's when you think you're not as good as everybody else.
Okay.
And you're, yeah.
So if any of you have ever had a feeling that everyone, that you don't really fit in because everyone knows more than you, or you're just an imposter, that's imposter syndrome. And all of us have felt that way from time to time. So it'll be an interesting thing to hear about. Okay, now, let's start where I want to start. Okay, so this was depth first search. And one reason we do depth first search is to get the pre-visit and the post-visit numbers. So I'm having a little bit of trouble here, so hold on a second. Okay. So there's depth first search. And one thing I skipped over when talking about depth first search was the analysis. So I want to come back and talk about that. Just to remind you how depth first search works, the key part of the algorithm is the explore. And what the explore method does is there's a vertex that you're exploring from, and essentially you visit every vertex that's reachable from that vertex. It hasn't already been visited. So you just follow every edge out of that vertex and explore the vertices that are connected to it. And you see that happening here. You go to explore vertex, mark it visited. We pre-visit. Then we consider every edge out of that vertex. So for each edge of that form, if it's an edge from V to U, if U has been visited, we visit it. If it's not been visited, we explore it, I'm sorry. And then we're done, we post-visit. So this loop here is what visits every neighboring vertex that has been visited. Of course, that will recursively visit every neighboring vertex that it has, and so on. And then depth first search simply visits every unvisited vertex. And we want to figure out the complexity of this. But before I do that, are there any questions I can answer about the algorithm itself? Well, I have a question for you. What form does this take? Which says for each edge of that form, do something. How do you find every edge of that form? What does that amount to? This is high-level pseudocode. So you're working on your caddis problem, you're going to have to implement this. How do you do this bit right here? Yeah.
Depends on which implementation you're using.
Okay, it says depends on which representation you're using for graphs. Okay, suppose you're using adjacency matrix.
So if you're using the adjacency matrix, then you have a list of all the nodes that are adjacent to you. So you just go through them and check if
Okay. So in adjacency matrix, you would go to row V, and this loop here would just iterate across row V, looking for entries that are not null. And when it finds it, or I guess not zero. If it's an unweighted graph, it needs zeros in it. So you're looking for a non-zero entry. And so you find one in column U, that means there's an edge from V to U. And then you work with it. So that means each time you hit this, you're iterating across one row of the adjacency matrix. Now, someone else tell me what happens if you're using an adjacency list. Yeah.
You just loop through all the nodes in the list.
Okay. So in adjacency list, you would have an array of length V. And at each entry in the array, at the entry for vertex U would be a list of the edges leaving vertex. Back up. You have an array here, index V gives you a list of all the edges out of V. And so you would be going down that list. Now, how long is that list?
As many neighbors as you have.
Just depends how many edges there are. So every list isn't the same length. Some of the lists may be empty if there are no edges out of a vertex. Other lists may be as long as V, if there's an edge to every vertex from this vertex. So that's how you implement that. So to analyze this, we have to count very carefully, make sure we don't overcount. So let's just start counting. That's not helping. Okay, that'll work. Okay, so first thing we have to do is initialize a visited array. So that's O of V. That's easy enough to see. We're just, the visit array is just a Boolean array, trues and falses, one entry for each vertex. So that's O of V. Okay? Then, we have to consider each vertex right there. And what I'm doing is instead of trying to analyze that entire loop, I'm just trying to break everything out. So you'll see what I'm up to in a minute. All right, now, over the life of one call to DFS, what happens? So we're running through this loop. So we're iterating through the vertices, so that's where that consider each vertex comes from. Then inside this loop, how many times do we check to see whether a vertex has been visited? V times. Right, that loop will run V times, and so that's O of V. Now, what about the cost of this explore? How many times do we call explore? From right there. How many times is that method call made? Yeah. Okay, it's called every time this is not visited, we find an unvisited vertex. Well, how many unvisited vertices will be found over the entire life of that call to DFS? Yeah?
The number of unconnected pieces.
Well, you said the number of unconnected pieces. That's true if it's an undirected graph. But if it's a directed graph, it's a little more subtle than that. It's hard to say in advance. Yeah?
So are you asking for just the explore call?
Yeah. How many times is this call right here made? Okay. It might be called once. It might be called V times. It just depends. If this first call manages to visit every vertex, that's the last call that we made from up here. We call it once, and that's the end of it. On the other hand, if this call doesn't succeed in visiting every vertex, the loop will find another unvisited vertex and call it instead. So it's hard to pin down an exact number. Now, how many times is pre-visit called? Again, now we're talking about the entire life of the algorithm. So we haven't talked about that yet. But over the entire life of the algorithm, explore will be called over and over again. How many times will that be called right there?
Explore times.
Okay? Say that again. Someone said the answer, I didn't hear what it was.
Explore times.
No, not how many times do you call previsit on the vertex? Yes. V times, once for each vertex. Okay? So explore will be called once per vertex. This method will be called once per vertex. Sometimes it's called from up there, sometimes it's called from down here, but it's called once per vertex. So we'll set visited of A to true V times. We'll set previsit to true V times. We'll call previsit V times. Next, what we have to do is, we have to enumerate all the edges. So every time the explore is called, we have to find all the edges from V to U. All the edges out of V have to be found. So some of them are found the first time explore is called, some of them are called the second time explore is called, but eventually they will be all, they would all be found. So over the entire life of the algorithm, how much work is done right here? Just finding the edges. Yeah?
That would be O of E. Or like to figure out all the edges that go from that line.
Okay, he said O of E. That's a reasonable guess. Not quite right, but what's wrong with O of E?
Overlapping.
Overlapping, meaning?
Yeah, some of the edges aren't going to be visited again. So the algorithm accounts for that.
Well, we're going to look. We need to look at every edge. We're eventually going to have to consider every edge, because that's what it does. We will consider every vertex. So this loop will be reached V times, once per vertex. And we're going to find all the edges out of V. The next time through, we're going to find all the edges out of another vertex. The next time through, we'll find all the edges out of the third vertex. Yeah?
So when you look at some edges twice?
You'll look at, if it's an undirected graph, you look at edges in both directions. But how much work does it take to enumerate all the edges? Forget about what happens inside the loop. Yeah?
O of V plus E.
Okay, O of V plus E, that's partially correct. What's your reasoning? Where does V plus E come from?
We go through every vertex and check all the edges.
Okay, so if you're using an adjacency list representation, yeah, every time through you will go to an entry for a vertex and follow its list of edges. That's going to be V plus E. But what if we're not using an adjacency list? Yeah? It'd be O of V squared in that case. So the cost of enumerating the edges depends on which data structure you're using. But it involves looking at the entire data structure. To find all the edges, you eventually have to look at the entire data structure. So I'm just going to call that right now the cost of enumerating all edges and leave it unbound. So we'll come back and figure out the cost of enumerating all edges. How many times do we check to see whether a vertex has been visited? Again, not each time through the loop, but over the entire life of the algorithm. This loop runs multiple times. How many times do we do this?
Many times.
Hmm?
Many times as the
Many times as the loop runs, but I need to do this in terms of V and E.
Would it be O of V squared again?
No, not O of V squared, yeah?
Is it O of E? Because you have to look at each edge once.
Yeah. For every edge that you found, you do this check. So it's O of E. Okay? Sometimes through you may be looking at fewer edges, other times through you look at more edges, but over the entire life of the algorithm that becomes O of E. Now, how many times total are these two method calls made? Over the entire life of the algorithm. Okay? Explore is called once per vertex. Some of the calls happen up here, and some of the calls happen down here. But we make that many calls. And how many times is post visit called? Okay, once per vertex. Okay? So I've sort of accounted for everything. Now, why didn't I just say, figure out the work of the body of the loop and multiply by v, since this loop runs v times once per vertex? Why not just decide, okay, at worst, how much work is done inside this loop? How many times is the loop called, multiply, and be done with it? Why do I instead, why am I doing this thing about saying, over the course of every call to explore, what's the total number of times visited is called? Why do I account for it that way? Right, well, let's try to do it that way. Let's consider one run of this loop. How many times is visited of u going to be called? How many edges are we going to find to look at in a given time through this loop? At most v, right? We can't find more than v edges. So we could just say, okay, that's O of v. And then say this whole loop does work proportional to v squared. But that's an overestimate because we're assuming the worst every time through the loop. Sometimes through this loop, there'll be a few edges. Other times there'll be a lot. We're not going to necessarily see a lot every time. So rather than try to think up the best case for this, the worst case for this and multiply by v, we're just figuring out the worst case for for the total work done by this and all calls to explore. So we had stuff up there that just happens once. All this other stuff was over the entire life of the call. So Explorer is called a bunch of times, but we'll end up doing this exactly v times. We'll end up doing this v times. We'll end up doing this v times. We'll have to enumerate the edges, and that means over the entire life of the algorithm, we've got to consume the entire data structure, depending on what it is. Then we're going to find e edges, which means that over the entire life of the algorithm, we'll do this once per edge. And over the entire life of the algorithm, we'll do these method calls right here, once per vertex. So that's where that all comes from. So what's left if we want to compute the complexity?
Add it up.
Yeah, add it up. Okay, so if we add it up, we got a bunch of O of V's and a bunch of O of E's. So we get O of E plus O of E, plus the cost of enumerating all the edges. And that depends on which data structure we're using, right? So what if we're using an adjacency list? It's going to be O of E plus O of E plus what? What's the cost of consuming an adjacency list? O of V plus E, which will simplify to what? Right, that's just going to be O of E plus V. And for matrix, we're getting O of E plus O of E plus O of V squared. And how do I get off simplifying O of V plus O of E plus O of V squared into O of V squared? What happens to the E term and the V term? Clearly, V squared dominates V, so that goes away. It's lower. What about the O of E? Yeah, E can't be bigger than V squared, so it simplifies. So that's our result, which we saw last time. We saw the result last time. We call it a linear algorithm because the time it takes to do a depth first search is proportional to the size of the data structure being consumed. You can't do better because you've got to at least look at all the data structure. Yeah?
I just want to clarify, so O of V plus E is different than O of V plus O of E?
I'm worried about my projector right now, so.
I think you fiddled with the wire.
Yeah, I touched the wire, but now I gotta wait for it to bounce back here. It's ridiculous when you can brush a wire and you lose your signal. All right, hold on a second. Okay, so what was your question?
I just was curious, so O of V plus E is different than O of V plus O of E?
Okay, so he's asking, is O of V plus O of E any different from O of V plus E? What do you think?
No.
I have a yes and a no. Yeah, they're the same thing. That's why we simplify like that. They amount to the same thing. Okay, now, so there's our analysis of depth first search. And now, before we go any further, I want to ask you a question. We have talked about using two representations for a graph. One is the adjacency. That's bad. One is the adjacency matrix, and the other is the adjacency list. Now, on the current caddis problem, what you have to do is represent a graph. You have to create a graph which represents cities and one-way roads between them. So first of all, what kind of graph is that? Cities and one-way roads. It's a directed graph. Furthermore, this problem says it's an acyclic graph. It's a directed acyclic graph. Which way should you represent your graph in the caddis problem? Should you represent it with a matrix, or should you represent it with a list? Okay, it turns out you want to use a list. Okay? Now, we have said, we've been working like, okay, if you use an adjacency list, you're going to have something like this. Let's say your graph, edge 0, vertex 0 has an edge to 3, an edge to 4, an edge to 6. So you've got it linked like that. And so if you want to know all the edges out of vertex 0, boom, you go to index 0 and then follow the list that's stored in there to find out what vertices you can reach. In the caddis problem, the vertices are not numbered, they're named, they're strings. So what do?
Use your index.
Use what?
You could use your index.
Use an index. What index?
Oh, well, no index.
Okay, so
You assign a number.
the names of the vertices are names of cities. Yeah,
Could you use a map?
right, you just use a hash map. So a hash map is basically a generalization of an array. An array, you just index, you think of an array as being indexed by integers. A hash map is just indexed by strings. So just turn that thing up there into a hash map. And then if you want to know what vertices you can reach from sync city, you just look it up in the hash map. And you'll get back a list of what? What should your list, what should be the, if you got a hash map now, the keys are strings, the names of cities. What are the values in the hash map? List of strings. Right. It won't be a list of events like this. It'll just be a list of strings. And you can go through that list and see the names of the cities you can reach. Okay? Now, depth first search requires a visited array. Keep track of whether something's been visited or not. And we've been assuming that we just create an array. And we store trues and falses in it, depending on whether we visited it. Well, those are vertex numbers. The caddis problem, we have strings. What should we do for our visited array?
Dictionary.
We could use another map that maps from strings to booleans. Well, a dictionary is a map. Hash map, I said hash map, but if you're using C#, it's dictionary. Same thing, yeah?
You could not use strings for the list instead and just like use the names, map the names to an index, and then use that index for both the list and the visited array.
Yeah, I mean, you could map the names to indexes and then just use these representations, but that's a sort of an extra layer of indirection. Yeah?
I managed to complete it without using a visited array,
Mhm.
and I had each one store its own condition of having been visited or not with the information. Like if a spot in your array is a list, contains a list, that's some sort of object, and I had that object also store
Okay.
a Boolean for it had been visited.
All right, so what he's saying is he made his graph representation more complicated so he didn't have a visited array. But why not just, that's fine, but why not just keep to the way I did it? What can you do for a visited array besides, yes, you could use a hash map, but I think it's something simpler to use. Yeah?
Boolean 2D array?
Well, not a Boolean 2D array, no? Yeah?
Could you just use a set?
Yes, use a set. Just keep a set of all the ones you visited. Right? 'Cause initially it's empty, and as you visit things, you add it to the set. That's another way. You got to keep track of pre and post numbers. Use a map. Yeah.
Would that not take more time through iteration the more you start adding to the set? Wouldn't you have to check if each one is in the visited set?
Okay, so he's saying, won't that make it more expensive because you've got to check to see if it's already in the set? We use a hash set, effectively constant time. Okay, so you can even though the vertices are strings and we've been pretending that they're ints, it's really easy to adapt the algorithm to this purpose. Adapt the representation to this purpose. And the algorithm doesn't really have to change at all, except instead of using arrays, you're using hash tables of various kinds. Okay? I just wanted to mention that before we went on, because you'll face that problem. Now, we talked about, at length, about doing depth-first search to compute pre- and post times. So let me just remind you how that worked. So let's suppose that we've got this graph here, and we're doing a depth-first search to get the pre and the post times. Okay, so we're going to I think it's really not working the way I want it to do. Anyway, we're going to do a depth-first search of this graph starting at G. So G got the pre-time of 1, and then we explored out of G, and F got the pre-time of 2. What's going to happen next? Yeah?
F gets the post time of G.
Right, there are no edges out of F to explore, and so we're through with F, and it gets a post time of 3. And then we return, the recursion returns to G, and G is looking for other things to explore. It doesn't find anything, so what happens? It gets a post time of 4. Then we pick somewhere else to start. So depth-first search would now be searching for an unvisited vertex to explore from. Let's say it picks E. So E gets a pre-time of 5. What's going to happen? Right, there's one edge to G, but it's already been visited, so we'll ignore that. Then we got to go to C. We try to go to C. It's not visited, so it gets a pre-time of 6. There's no way out of there, so it's a post-time of 7. We looked at everything out of E. It gets an 8. Then let's say we visit D next. It gets a 9. Going to E is fruitless because it's visited, so it tries to go to B. That's unvisited. It gets a 10. There's no unvisited vertex to visit, so it gets the 11. We return to D. It gets a 12. And then we finish up with A. So that is one way that a depth-first search could unfold on this graph, and one way that the pre and post times could be assigned. Yeah.
So I noticed that we do a lot of comparisons with post times. Do we do anything with pre times?
Okay, so he's saying, yeah, so we really haven't found a use for pre times, except pre times essentially can stand in as visited. So if a vertex has a pre time, that means it's been visited. Now, what was the point of doing a depth-first search like this? Why are we doing it on a DAG? What's the reason to do a depth-first search on a DAG? Yeah?
You could see like an order to iterate through the nodes for dependencies and stuff like that.
Okay. We do it to topologically sort the DAG. So a topological sort is a list of vertices that have what property? Say it louder. Okay, so roughly thinking, the list starts with the sources and ends with the sinks. It starts with a source and ends with a sink, that's guaranteed. And every vertex occurs before all the vertices that are reachable from it. And we saw last time that once you've done a topological sort, if you just order the vertices in reverse, in descending order of post time, I mean, once you've done a depth first search, if you order the vertices in descending order of post time, then you've got a topological sort. So this is the sort that comes out of that graph up there, out of that. See, A has the highest post time, D has the next highest, B, and so on. And what you see is you pick any vertex, like D, we're guaranteed that every vertex that is reachable from D comes after D in the sort. So you see that? Every vertex is reachable from D except A, and so the occurs after D. Now what about C? Does it have that property? Does every vertex reachable from C come after it in the sort? Okay, I heard a no. What vertex that's reachable from C does not come after it in the sort? Yeah?
All the vertices that come after C
Well, what vertices come after C?
in the list.
Okay, E, all right. What I claimed was that every vertex that's reachable from C comes after it in the list. I did not say every vertex that comes after C in the list is reachable from C. Okay? So, there's C. Is every vertex that's reachable from it occurring after C? What vertices are reachable from C? None. So it really doesn't matter what follows C. All the ones that are reachable from it are after it. Those aren't any. Okay? Now, we could do the depth first search in a different way. We saw this last time. Let's say we start and we do things, we consider vertices in alphabetical order. So we start, A gets the first one. What will get the next pre-time? So we visit B just because we're doing alphabetical order. From B, we're going to go to E, because that's the only one reachable from B. It gets the 3, C gets the 4, then we're stuck, so it gets the 5. We back up to E, and then we go to to G. It gets the 6. We go to F for the 7. We're done with A, with that, we're done with G, we're done with E, we're done with B, and now we're back to A, and what happens? We go to D, we're done with it, we're done with A. And we get that topological sort, which is a little bit different. It starts out the same, A, E, B, E, and the C, F, and G are in different order. That's another topological sort. Yeah?
So, just for clarification, the arrow going from the edge going from A to D, should that arrow not exist, that would mean that A and D would tie in place for which would go first?
Okay, so he's asking, suppose there was no edge from A to D. Okay? What would that say about possible topological sorts? So with the edge there, is there any way D could come first? No. Because D has to come after A. But without the edge there, A could come first or D could come first. It would just depend which had the higher post time. So there'd be more possible topological sorts. With this graph, there's 3 ways to sort it. As you start taking edges out, there becomes to be more ways to sort it. What if there are no edges at all?
Right. Factorial ways to sort it.
It's just, right, there's going to be, b factorial ways to sort it. So there's going to be a lot of ways to sort it. So the fewer the edges, the more flexibility that you have. Now, when you implement an algorithm on DAGs, you almost always want to first do a topological sort of the vertices in the DAG, because that makes the algorithm easy to write. And I've been poking around on Caddisq like I normally do, and I'll look and I'll see solutions that aren't running in time or are getting wrong answers. Invariably, they're not doing a topological sort. For this Caddisq problem, do a topological sort. It's not hard. I gave you the algorithm. Now, how complex is a topological sort? What's the cost? Maybe you're not doing a topological sort because you think it's too expensive. Yeah?
Linear with respect to the data structure.
Okay, he said linear, it's linear in terms of the size of data structure. It's just a depth first search, right? We do a depth first search, and we already saw the cost of that. But there's an additional cost hiding. What do we have to do other than the depth first search? Yeah.
You have to sort the post tags?
We got to sort by the post times, and they're V vertices, and if you sort with merge sort, let's say, that's going to be V log V. So what it looks like is, we do a depth first search, and then we sort vertex by the vertices by post number. And that means, for a matrix, it's the V squared time for the depth first search plus the sort, we get V squared. On the list, it's a little bit worse. It actually is no longer linear. Can we do better? How can we do better? Yeah?
Create the sorted list as you're traversing through.
Okay. You can just create the list as you're traversing. So one way to think about that is, one number is going to get its post time first, right? And that'll be the smallest post time. As soon as a vertex gets a post time, just stick it at the beginning of a list. The next vertex that gets a post time, add it to the end of that list. Just build the list as things get post times. So rather than collecting the post times and then doing the sort, just make it so that when you post visit a vertex, you add it to the list. Then when you're done, you won't have to do a sorting phase. You already have the vertices. Another way to look at it is, don't forget about the pre-times, just record the post times. And then those post times become the index where you should store something in the array, or I guess the reverse index where it should be stored.
But then you would still need a visited for each.
Yeah, you still need a visited in that case. But don't think that you have to do the topological sort, do the depth first search, and then do some sort of sort of the vertices by post time. You can generate the list as you go and keep the algorithm linear. Now, what I find, we looked at this last time, what I find is that I think students just don't believe me when I say that it's a lot easier to do an algorithm on a DAG if you topologically sort it first. And they think, I don't need to do that, that's an extra step. But it really does make things easier. And I want to go over the example again, the 3 examples that I showed you. And let's talk about it. And I'm going to talk about the caddis problem too. So here's the spreadsheet update problem. The dependent on relationship in a spreadsheet you can view as a DAG. So we have each vertex represents a cell in the spreadsheet. The thing in the circle is what's stored in that cell. And the arrows are the dependency relationship. So this just tells us that this vertex here, well, rather, this vertex is dependent upon by D and by F. Okay? And sometimes it'd be helpful if the arrow is pointing the other way, so you can imagine wanting to have a reverse of this graph as well. Because when it comes time to do that plus operation, you need to be able to find your predecessors in the graph. But the edges have to go one way or the other. The problem is, suppose something changes in the graph. In what order do we need to recompute the values? So the numbers written outside of the boxes are the values of the cells, the things that are actually displayed in the spreadsheet. So what is that order? If, say, okay, so right there I changed I'm sort of stuck in this land where it won't go backwards for me. I don't know what's going on. Let me try again. Okay, suppose that 2 changes to a 7. Suppose A, instead of containing a 2, in the white area contains a 7. What cells need to be reevaluated?
The plus. Multiply.
Okay, well, first of all, A needs to be reevaluated. It's displaying a 2, and internally it's a 7. We've got to change this cell. What else has to change?
B, F, C.
B, F, and C. So to change. So basically, any vertex that's reachable from here in a depth first search needs to be reevaluated to reflect this change. It needs to flow through the graph. And students are tempted to write some sort of recursive algorithm that follows every possible path and updates the vertices The problem is so by path I mean every possible combination of edges. But there can be an exponential number of possible combination of edges. What we want to do is a simple calculation on each cell that's non-recursive. So what is the calculation we need to do on vertex A to update it? So when that 2 changes to a 7 internally.
Just update the value.
Right. If your cell changes to a constant value, now the value of the cell is just that value. So the 2 changes to a 7. What has to happen to reevaluate this times? Yeah? You have to look at the calculated value of this cell, the previous 2, this one and this one. So essentially, what you would have to have is a reversed version of the graph. So you could quickly find the cells that you depend on. You look at their values here, and you multiply them. Okay? Down here, we have to look back at this cell and that cell and add them. So the simple calculation you do for an operator cell is just you look back at your predecessors, get their values, and do the operation. So what's wrong with that changes to a 7? So that's... So internally that's become a 7. Why don't we just start right here, reevaluate this? What's wrong with just running the plus right now?
Because 14 and B and F haven't been updated.
Right, these haven't been updated. So if we run the plus, we'll say, okay, 14 and 35 is 49. All right? And some students, they see this and say, oh, I'll just recursively compute the value of everything that's reachable for me. So they end up doing sort of a depth-first search, in a sense, trying to recompute values in the right order. But the topological sort gives you the right order to evaluate the cells in. So that when it comes time to evaluate a cell, all the ones that it depends on have already been evaluated. That is the point of the topological sort. So here is a possible topological sort, A, D, F, B, C. And let's just evaluate in that order. So reevaluate A. What should its value be?
7.
7. Next, on this list down here, it says to reevaluate D. Okay? So to reevaluate D, we just look up the value of A that's previously calculated, and we look up the value of E, which was previously calculated. And it's 7 and 5. And we add them. We don't have to recalculate anything. We just look up a stored value. Okay? Now it says to look at F. So F looks back and says, okay, I got to multiply 12 and 5, and it gets 60. B says, all right, I got to multiply A and D. It gets 84. And then C looks back and says, okay, I got to add 84 and 60 and get 144. So we did the depth-first search to do the topological sort. And then we do a simple calculation, non-recursive, boom, 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 on the vertices in topological order. And we fill in the values, we update all the values that need to be updated. Yeah?
And in order to know the 2 predecessors, you need to use the list.
Okay, so to find the predecessors, so for this particular algorithm, to find the predecessors, you would be advised, before you do anything else, to take the graph and reverse it. Just create a new graph where all the edges point in the other direction. Just iterate through the graph representation and use that to build a new graph where all the edges point the other way. That way you can easily go backwards. Yeah?
What about the previous DAG, the one where the node like C doesn't touch anything else, but is before was before F and G in the topological sort? Would that also update F and G, even though C is not have an edge that reaches to?
Well, let's look at this. What happened to E right here? We did not do anything at all with E. Why not? First of all, why is it okay to exclude E from the reevaluation? Yeah?
Not reachable by A.
Yeah, it doesn't depend on anything that's changed. How was it that the topological sort didn't find E? Yeah?
It started at 8.
Yeah, he said because it started at 8. I really didn't do a full topological sort. When you do a full topological sort, you do a depth-first search, which makes multiple calls to explore. I just did a single call to explore beginning at this vertex. And it only found the vertices that matter and put them in order for you. And now I don't even have to worry about that one. And that's a big win. That's a big deal in this, in a real spreadsheet, because typically you change one cell, only a few others matter, get affected. You don't reevaluate everything else in the graph. Okay? So, do you agree that the calculation done at each vertex is simple and non-recursive? I mean, if you're going to implement this algorithm, you would have to have some way of storing for each vertex this white number here, the value. And then the operation you do at each vertex is just you go look up the value of D, look up the value of E, which has magically been previously computed. Multiply it, and that becomes your value that you're storing. The topological sort just keeps things flowing in the right direction. Okay, this is another one we looked at. Number of paths leading from a source to a vertex. So it says right there are 6 paths where there's 6 ways to get to F starting from a source. Okay, can you find the 6 different paths? What would be one path to get from A, which is the only source, to F? You go to A, and then where do you go? Say B, A, B, E, C, G, F. That's one way. What's another way?
A, B, E, G, F.
A, B, E, G, F. Or A, D, B, E, C, G, F, and so on. But it turns out there are 6 ways. So the problem is, given the graph, compute those numbers that are up there. All right? So let's see. Let's wipe that out. And we do a topological sort. And here's my simple computation. If a vertex is a source, there's only one way to get to that source from a source, right? If you start in a source, there's only, if you're trying to get to V, you'd better start in V, and then you're there. If you start anywhere else, you can't get there because it's a source. So paths of V is 1. And then paths of V, this is just saying, well, read this to me. I think some students may see this sigma here and run for the hills and think, like hell, that's a simple solution. But what is that in programming terms?
Summation.
It's a loop. It's a sum. It's a loop that sums some stuff up. So what's being summed up? You're trying to find how many ways there are to get to V. Yeah?
The predecessor's values?
Right. So how many ways are there to get to E? Well, it's the number of ways there are to get to D plus the number of ways there are to get to B. You take every way there is to get to D, you can turn it into a way to get to E. You take every way there is to get to B, you can turn it into a way to get to E. So we just add up the path's value of each vertex. So this just says loop through all the edges from a predecessor to V, the thing you care about, and add up their paths. So again, you need to reverse the graph. So if you want to know how many paths there are to E, or let's say paths are to G, you would say, okay, how many paths are there to C, how many paths are there to E, add them up, done. That's what that says. Yeah?
So I can see how this would be useful for like other algorithms, but it doesn't seem like it's useful in ours. Is that true? Like not topologically sorting, but specifically counting the number of paths.
Oh, no. Just like the one before. It's a different problem. The concept, topological sort's important.
Okay.
But your problem's completely different. So there's a topological sort. And let's see how it works out. We start with A, so what number do we stick with A? What's the program say to do? 1. And then we look at D. So it says look back at the predecessors in the graph and add up their values. So what do we put with D?
1.
It's only got the one predecessor, and it's a 1. Okay? There's only one way to get to D from a source, so that's right. What number do we put with B?
2.
Right, we look back and there are two predecessors, we add the 1 and 1, we get 2. Is that the right value? Are there two ways to get to B?
Yes.
Yeah, either through D or directly from A. Okay, and then for E, we just add up the 2 and the 1, we get a 3. C, it's just the 3. G is the 3 plus the 3, that's 6. F is 6. You just go do the topological sort, zip right through. This calculation for each vertex is this one. It's just a conditional. In code it would be if I'm a source, the answer is 1. Otherwise, loop through my immediate predecessors and add up their values. Okay? Here's one that's more like the caddis problem. It's not exactly the caddis problem. We're going to give every vertex a price. And that's the white label. And we're going to compute a cost. And I'm going to call the cost of the vertex the highest price reachable from that vertex. And that's what's displayed in yellow. So you're given the prices, you've got to compute the costs. So why is the cost of F, why is that yellow number on F 2? Remember, the price is the highest, the cost, the yellow number, is the highest price reachable from you. Yeah?
F can only reach itself.
Right. The only thing reachable from F is itself, and so it gets its price and cost are the same. On the other hand, why does A have an 8? Well, actually, there are lots of things reachable from A, but it turns out that its 8 is biggest, so it has an 8 because it itself is 8. But how did D get to be a 6, even though its price is 2? Because you can reach C from there, it has a 6. So the problem is, wipe out the yellows and have an algorithm to fill them back in. So what's the algorithm? What's the first thing you should do? Topological sort. Then you've got to figure out two things. What order do I go through the topological sort? Sometimes it makes sense to work from the left to the right, sometimes backwards. And what is a computation I do with each vertex? So in what order should we fill things out? Should we fill things out, should we write the yellow numbers in starting with the source and working toward the sink, or the other way?
Right to left.
It makes sense to work backwards. Because before we compute A's cost, we have to know the cost of everything that's reachable from it. So it makes sense to start with the sinks and work backwards, because we can solve the sink right away. Once you've solved F, you can do G. Once you've done G, you can do C, and so on. So we need to do this one in reverse topological order. And what is the simple computation we do for each vertex?
Find the maximum value of itself and its other paths.
Okay. So let's take E. You take the max of the cost of everything reachable from, not everything reachable, of the direct neighbors. So you take these two edges and you say, okay, that's a 6, that's a 2. You take the max of those and the max of that. So you take the max of the 6, the 6 and the 2, I'm sorry. You take the max of the 1, the 6 and the 2, and you get the 6 here.
I'm sorry. Why are you comparing the prices and not the costs? Like for E, why aren't you comparing the cost of the yellow 6 and the yellow 2 and then making
We are.
instead?
So to compute this yellow 6 right here, I have to look at that yellow 6, because that's the cost of C. And I got to look at the cost of G, but I got to look at my price.
Okay.
All right, so I look at all the costs of my descendants, my direct descendants, but I'm trying to compute that yellow value. So I take the max of this one, the white one, and these two yellow numbers, and I get a 6.
Okay.
And so that's what that says right there. It's a loop. Basically, you're looping, taking the max over some edges. And let's see how it works. So we do the topological sort and reverse it this time. And that gets a 2. What does G get?
2.
We got to take the max of yellow 2 and white 2. So we get 2. Then we do C. So it takes the max of yellow 2 and white 6. Then we do E. We take max of yellow 6, yellow 2, and 1, so that's 6. And then, yeah, now it's gonna work out. B, we take the max of yellow 6 and white 4. D, we take the max of yellow 6, white 2. And then A, we take the max of yellow 6, and white 8. And so we work backwards. And again, this is non-recursive operation at each step. And that operation is based on previously computed values. And how do we know that those values will have been previously computed? Because we're doing things in topological order, or in this case, reverse topological order. Okay, let's take a break.
Finish, Bob?
All right, now, the caddis problem, if you haven't looked at it, imagine you have a bunch of cities, and they're named after these letters here. And each city has a toll. So to enter city C, you have to pay $1. To enter city A, you got to pay $100, and so on. And then the arrows, the edges, represent one-way roads between cities. And this city is, the roads are guaranteed to form a DAG. There are no cycles. And so the problem is, given a pair of cities, tell me what's the cheapest way, I'm not tell me the cheapest way, but what is the least amount of dollars you have to pay to get from that city. So what would be the answer for A and G? So to get from A to G, your best deal would start at A, then go to C, that costs $1. You go to D, that's another 2, that's 3. Go to E for 4, and then to G for 6. If you go if you start by going from A to B, you've already spent $6, and you're not going to do any better. Okay, so that's the game we're playing. So we've got to view this as some sort of computation on the DAG. So how can we do that? Certainly we're going to do a topological sort. Yeah?
Depth research.
No, we're not going to do a depth, we're going to do a depth first search in the form of when we do the topological sort. But at that point, we're done with any searching. Now we're just going to do a simple calculation on each vertex in some order, either in topological order or reverse topological order. Yeah?
You just start at whatever one you're looking at and find the cheapest way to go, or where you can reach from there.
Okay, suppose I was interested in finding the cheapest way to get from A to G. See, I've got to view this as a problem that I can solve at each vertex. So we sort of have to restate the problem slightly. Yeah?
You just kind of go through and say what's the cheapest way to get to B from A, and then C from A, and then D you would do the exact same thing, but from B and C.
Okay, I'm going to propose a different way. So he's saying, why don't we first calculate he was going in forward direction. I'm going to suggest going backwards. Okay? I'm going to ask the question, what is the least amount of dollars you have to pay to get to G from every city? Okay? Yeah?
So you'd start from G.
All right, right, so we'd start from G, and what's the cheapest way to get, in fact, I'm going to add another one here. I'm going to add H here. I'm going to make it 5. Okay. If you start at G, what's the cheapest way, what's the cheapest price to get to G? What? Yeah?
$2.
No.
No, $0.
The toll is for entering the city. Okay? So if you start at G, how much do you have to pay to get to G? Yeah?
0.
0. So I don't know where I'm going to write that. I'm going to write it here and put it in the box. So that's what it's going to cost you at a minimum to get from G to G. Okay? What about H? What's it going to cost you to get from H to G?
You can't.
You can't. So I'm going to call that infinity. Can't do it. All right? What about from A to G? What's wrong with asking that question right now? Because that depends on the cost of getting from B to G and C to G. I don't know if those are yet. What's the natural way to work on this? Reverse topological order. We solved the sinks or the base cases. We solved them easily. So let's work backwards in topological order. So what can we do next? For which of these vertices do we already have the subproblem solved for their successors? F and E. F or E could come next in the reverse topological order, because they only depend on G and or H. So let's do F. So how do you decide what to write as the cheapest way to get from F to G?
The only way.
Yeah?
It's the sum of the value to enter the city and the value the city has.
Right. That's the cheapest way to get from G to G. This is the cheapest way to get from H to G. So I take the smaller of these two values. Well, no, actually, that's not exactly what I do. So if I take this route, what's the cost going to be?
$2.
That's 0 plus 2. And if I go this way, what's it going to be? That infinity plus 5. So I've got infinity if I go this way. I've got 2 if I go that way. So I go that way. So it becomes a 2. So this is the simple calculation you're doing in each vertex.
And it's not, you can't just measure to the neighbors first and then say take this minimum of the two, because like a cheaper path might lead to a more expensive path, so you have to go all the way to the goal, right?
No, we just look at our neighbors. We've already found the cheapest way to get from H to G, and we found the cheapest way to get from G to G. We only got 2 choices. We either got to go to G and then follow the shortest path to G, or we got to go to H and follow the cheapest path to G.
What if we had a case where there was a city in between us and our goal?
Well, we'll work backwards. We'll get a case like that shortly.
Okay.
So look at, next in topological order would be E.
That will also be 2.
Okay? It's only looking at one neighbor. So it's going to take the 2, and it'll take that solution, add the entrance toll for G, and we're going to get a 2 right here. Okay, what would come next in topological order?
D.
D. And it's just looking at E, so it takes the 2 for E, adds the entrance tool, which is 1, and gets a 3. What would come next?
C.
Either C or B. So let's do C. What's C going to do? It's going to say, okay, to enter the city it costs 2, and then it will cost 3 more to finish the job, so that's 5. Or it's going to take 5 to enter this city, plus 2 to finish the job, that's 7. So I should go in that route. So that's 5, right? I don't have to look beyond my immediate neighbors, because I've already solved the problem for my immediate neighbors.
So what if E had a value 100? And then we chose to go down D instead?
Well, if E had the value 100, D would have a huge value too.
I see.
See? The information is propagating backwards. But the thing you've got to be convinced of is that when it comes time to calculate for a vertex, you just need to look at the immediate successors, because you've already computed the answer for them. People are tempted to keep searching all the way to the end every time, and that's a waste of time and it's totally unnecessary. So what about for B?
Compare 3 and 2.
Right. You've got 2 ways to go. If you go via D, it's going to cost you 2 to get into D, plus 3 to finish up, so that's 5. If we go the other way, it's going to cost you 1 to enter E, plus 2 to finish, 3. So that's the value for B. And what about A?
It's going to compare 1 plus 5.
Right. 1 plus 5 is 6. 3 plus 6 is 9. I like the 6 better. So I get a 6 right there. And I'm done. Now, suppose this was a massive graph. Would you need to do the, when could you stop with this process? Suppose you're interested in the cost of getting from A to G. As soon as you get A, you don't need to keep, suppose there was stuff back here to the left of it. You don't need to keep going once you get the answer. Okay? Yeah?
Could you also stop at A's, the places A points to?
Well, we got to calculate the value for A. So, I mean, you can't skip A. So suppose the way the problem is written, you get a graph, and then you get a bunch of questions. A to G, C to E, B to A, whatever. And you've got to answer all those questions. How many times do you need to topologically sort the graph? Once. There's no point in sorting it over and over again. You get the same answer. What do you have to reset every time? Yeah, you've got to get rid of these boxes and recompute them from scratch. But you don't have to keep topologically sorting the same graph. Yeah?
To reconstruct the path, do you make another pass, or do you pass the information about?
Okay, he's asking about reconstructing the path. You don't have to. Yeah, to reconstruct a path, that makes it a little more complicated. I won't go into that, but for this problem, there's no need to. All you output for A to G is this 6. You don't have to say how to do it. You just say what it is. Yeah?
Now, by doing the topological sort, you're accounting for the fact that, let's say there was a branch towards C that was not from A.
Mm-hmm.
You would have kept going that way because you would have thought A might be further down that way.
Yeah, so let's say there was something like this. You may have, I mean, if that was the situation, you may end up calculating the cost of getting from, depending how the topological sort went, you may end up computing this one, even though you don't need it. So you just keep calculating until you finally do A. So if you did A first, you wouldn't need to ever calculate X. Yeah?
To get like the predecessors, do you just use a linearization, or do you have to reverse the graph?
Okay. So we decided that we want to do this in reverse topological order, right? We want to work from sinks back to sources. So we could do it in reverse topological order. And then what else? Do we need to reverse the graph?
No.
Okay. Why is it we don't need to reverse the graph here? What is it about this graph?
Because its dependencies are already pointing towards it.
Right. To calculate this box here, we don't care what's back this way. We just care about these 2 edges out. So we don't have to reverse it. It's got the arrows pointing in the right direction already. So all you have to do is be able to represent a graph, which I told you how to do at the beginning of class. Just use hash tables. You have to know how to do topological sort, which we talked about. And then you just apply this operation at each vertex. But everyone's not here, and I guarantee you people are going to be doing all kinds of weird things all week. But hopefully you guys will. Yeah.
Is this similar to the A-star algorithm?
Well, he asked, is this similar to the A-star algorithm? We're going to study Dijkstra's algorithm, which is similar. And this would be Dijkstra's algorithm except the totals are on the cities instead of on the edges. If the totals were associated with the edges, then we could use Dijkstra's algorithm. And you could solve this. You could adapt this and solve it using Dijkstra's algorithm, but I think you should solve it as a DAG problem. It comes up a lot. Yeah.
So it seems like the benefit of using topological sort as opposed to Dijkstra's is you have multiple, I guess, problems that you can use on the same topologically sorted.
That is true. You can reuse the sort. And also, you know, getting away from this problem, there are plenty of DAG problems that you couldn't solve with Dijkstra's algorithm.
Which one would perform faster in this case? Between
They'd be the same. Be linear time. Although I take that back. Dijkstra's algorithm.
Because this one you have to sort it. Well, you only sort it once, right?
Well, you do a topological sort, but that takes linear time. But Dijkstra's algorithm uses a priority queue, which gives you makes it a little more complex. And this actually is asymptotically faster. Okay. Any last questions about this? Yeah.
When you say reverse topological order, you just mean going from right to left instead of left to right.
Right. So topological order, you go from highest post time to lowest post time. Reverse, you just go from lowest to highest. Okay. Now, we won't have time to finish this topic, but I've been trying to bring it up for a week and a half now, so I want to start with it. So, I have previously argued that if you're sorting an array of size n, it takes at least linear time in every case. In other words, sorting is omega of n. Okay? Actually, when I say sorting is omega n, what that really means is that it will take linear time in some case, but it will also take linear time in every case. Why is that? What's the proof that sorting requires linear time? Yeah?
Because with comparing, you have to compare every element of the array to be sure it's sorted.
There's a more, yeah, but there's more, you can answer the question without talking about comparing. So yeah.
Because you have to touch every element.
Yeah, you've got to at least look at every element. You can't sort an array without looking at the elements. We're going to prove a lower bound on comparison-based sorting that's tighter. So there are sorting algorithms like radix sort, which runs in linear time, in the worst case. But it does its work without, it does things other than compare the elements. It takes the elements apart. It's not general purpose, first of all, and it works by decomposing things into bits. If you assume that all you can do with your elements are exchange them and compare them, you can actually prove that every sorting algorithm has to have an n log n worst case, or worse. You can't find a linear time sorting algorithm. So the idea here is to prove that. So let's start with the proof. We're going to do the proof by building a decision tree. So imagine you're doing insertion sort on an array that contains A, B, C in that order. So I'm going to draw a picture here. This is the current order of the elements. And these are all the possible outcomes. So when we're done sorting, maybe, depending on how A, B, and C compare, we don't know what numbers they really stand for, the A, B, and C be sorted that way, or maybe it will be that way, or maybe it will be that way. So basically there are 3 factorial ways the sort could turn out. We don't know right now. So we're taking sort of an all-knowing view of the sort. So what's the first comparison that insertion sort will do? What 2 elements will it compare? Yeah, the first 2. So it's going to compare A and B. Okay. going to ask, is B less than A? And the answer is either a no or a yes. Now, if the answer is no, how will that array be changed? Will it still be ABC or will it be BAC? It'll still be ABC. If B is not less than A, it's not going to move B to the left of A. Which of these other possibilities will still be in play? Yeah. Anywhere where A is to the left of B is still a possibility. So that one there and that one there. And so, you know, we're taking this all-knowing view. And if the answer is no, that's what the algorithm still has the array sorted that way. We know that there's these two possible outcomes. Okay? What will happen next? What two elements will be compared next?
C and A.
It'll compare C and A now. That's just the way insertion sort works. It's dealt with the second element, now it's dealing with the third. No, I'm sorry, yeah, not C and A. It's going to try to push C to the left, so first we'll compare C to B. And if C is less than B, will anything change? Will anything get swapped? If C is not less than B? No. Nothing will be swapped, and at that point we'll be done with the sort. Now, what if C is less than B? What will the algorithm do? It'll swap C and B. So the actual array will change, and we'll be in this situation, but there's still another possible outcome, depending on the answer to the next question, which is what? The next question will be, is C less than A? And depending on the outcome, there's two possible sorts. So what we're doing is we're tracing through what could happen when the array is sorted. And we could do the same thing on the other side, and I will go through that fast. That is called the decision tree for insertion sort if you're sorting a 3-element array. This is everything, this shows you everything that can happen when the array is sorted. Every path the logic can take in terms of the comparisons. How many possible outcomes? Look at the leaves of this tree. Why are 3 factorial leaves? Right, that's how many possible outcomes there are. That's how many ways there are to permute the 3 elements. What does each branch from root to leaf stand for? It's a particular way the comparisons can come out. So these are the ways the comparisons have to come out if you're going to end up with this sort. These are the ways the comparisons have to come out if you're going to end up with that sort. So imagine if we did this for an array of size n. What would the decision tree look like? There'd be n factorial leaves, and there'd be some branches. What would the shortest branch be? N minus 1. What's that correspond to? The best case. Right? So short branches are the best case. Long branches are the worst case. Short branches have the fewest comparisons. Long branches the longest, the most comparisons. So for insertion sort, you'd expect to find some that are short, n minus 1. Others that are long, like 1/2 n squared or something, because that's the worst case. One final thought, and we'll finish this next time. What if we did it for merge sort? What would the tree look like? Yeah?
It'd be the same depth.
Wouldn't be exactly the same, but it would be pretty well balanced. Almost perfectly balanced. What if you did it for the world's best sorting algorithm? Yeah?
It would be like a balanced tree.
It would be perfectly balanced. So this is how we can attack putting a lower bound on sorting algorithms. We can talk about decision trees and their shape without having to actually build them. We can imagine what the best sorting algorithm in the world, what its decision tree would look like and reason about it. We'll finish this next time.